Assalamualaikum. My name is Nur Afika binti Nur Muhammad Jilis. I would like to explain about what is resonant in AC RLC series circuit. Resonant in AC circuit implies a special frequency determined by the value of resistance, capacitance, and inductance. For series resonant, the condition of resonance is straightforward and it is characterized by minimal impedance and zero phase. When the curve for inductive reactance are placed on top of the curve for capacitive reactance, the point of intersection will give the series resonant frequency point. Fr or omega R is shown in the series resonant circuit where frequency is in hertz and impedance is in henries and capacitor is in farads. Electrical resonance occurs in an AC circuit when the two reactants which are opposite and equal is cancel each other out as XL is equal to XC. And the point on the graph at which this happens is where the two reactants curve cross each other. In a series resonance circuit, the resonant frequency Fr point can be calculated as follows. SL is equal to Xc, which is 2 pi FL equal to 1 over 2 pi FC, and follow the formula below. It can be seen that at resonance, the two reactants cancel each other out, thereby making a series LC combination act as a short circuit with the only opposition to current flow in a series resonance circuit being the resistance R. In a complex form, the resonant frequency is the frequency at which the total impedance of a series RLC circuit becomes very real, so there is no imaginary impedance exists. This is because at resonance they are cancelled out, so the total impedance of the series circuit becomes just the value of the resistance, and therefore is Z equal to R.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ashraf Afiq bin Jamil, and I'm going to continue about the explanation what is resonance in AC RLC series circuit. After the resonance are cancelled out and the total impedance of the series circuits become just the value of the resistance, then at resonance the impedance of the series circuit is at its minimum value and equal only to the resistance R of the circuit. Since the current flowing through a series resonance, the product of voltage divided by impedance at resonance, the impedance Z is at its minimum value, which is equal to R, and therefore the circuit current at this frequency will be its at maximum value of V over by R as shown at the figure below. Next, as for the frequency response of the circuit current magnitude above relates to the sharpness of the resonance in a series resonance circuit. The sharpness of the peak is measured quantitatively and is called the quality factor, which is Q, of the circuit. The quality factor relates the maximum or peak energy stored in the circuit, which is the reactance, to the energy dissipated the resistance during each cycle of oscillation, meaning that is a ratio of resonance frequency to bandwidth, and the higher the circuit Q, the smaller the bandwidth, which is Q equal to Fr, which is frequency, over by bandwidth.
The relationship between resonance, bandwidth, selectivity, and quality factor for a series resonance circuit can be defined as shown in the slide. There are a few formulas. The first one is resonant frequency, the second one is current, and then lower cutoff frequency, upper cutoff frequency, bandwidth, and the last one is quality factor. In summary, for resonance to occur in any circuit, it must have at least one inductor and one capacitor. Resonance is the result of oscillation in a circuit as stored energy is passed from the inductor to the capacitor. Resonance occurs when XL is equivalent to XC and the imaginary part of the transfer function is 0. At resonance, the impedance of the circuit is equal to the resistance value. Circuit current becomes maximum as impedance reduces. Voltage across inductor and capacitor cancel out each other, so voltage across resistor will be equivalent to supply voltage. At low frequencies, the series circuit is capacitive as Xc is bigger than Xl. That gives the circuit a leading power factor, while at high frequencies, the series circuit is inductive as Xl is bigger than Xc. This gives the circuit a lagging power factor.
Assalamualaikum and a very good evening. My name is Muhammad Izzat. So this current slide is an explanation for calculation AC RLC series resonant. So you can see I draw a circuit which consists of R, L and C. The value of R is 30 ohm, L is 100 millihenry and C is 40 microfarad. So this circuit have two conditions: normal frequency and resonant frequency. For normal frequency, you have to find three values: Xc, Xl and Z. So Xc is equal to 1 over 2 pi Fc, and you get the answer 66.315 ohm. Xl is equal to 2 pi Fl, and you get the answer 37.699, and Z is equal to 41.459. You also must have to find the value of VRMS. VRMS is equal to Vp times by 0.7071, and you get the answer 10.607. So for the resonant frequency, this condition state that XL is equal to Xc and Z is equal to R. So the first step, you must find the value of omega. Omega is equal to 1 over cert LC, and you get the answer 500 rad per second. And then you find the value of resonant frequency. Fr is equal to 1 over 2 pi cert LC, and you get the answer 79.577 Hz. For both XL and Xc, you are using the same formula, but you change the value of normal frequency to the resonant frequency. And both of them, you get the same answer, which is 50 ohm. This condition states that Z is equal to R. So I made the calculation, and it is proof that Z is 30 ohm, which is same to the value of R, which is 30 ohm also. And next is I find the value of I. I is equal to Vm over R. Vm is 10.607 divided by R, 30 ohm, and you get the answer for I is 0.353 ampere. So lastly, you find the value of voltage VL and VC. VL is equal to omega Li, and you get the answer 17.65, and VC also you will get the same answer with VL 17.65. Okay, that's all.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Hadi Syazwan bin Harman. Okay, today I would like to explain about simulation of series RLC circuit in resonance state. Okay, firstly we must draw a simple circuit of series RLC, which in series that RLC component we must draw in one line. Okay, you can see here that we put the resistor 30 ohm, inductor 100 millihenry, capacitor 40 microfarad, and also in AC supply we put 10.6 607 VRMS and frequency 79.577 Hz. Okay, how to get voltage output? Firstly, the step is must to connect the multimeter to each component. Must to connect the multimeter to each component, and also at the R1, L1, and C1. Okay, how to get the current output? So, to get the current output, we must also put the multimeter here and connect to the line. Also, we remove this line. Okay, the setting is we must to click at the multimeter, and set to the voltage and sine wave. Also, same way to the inductor and capacitor, we must to click at the voltage and sine wave. Okay, to setting at the current, we click at the ampere and sine wave. Okay, let's run. Okay, after run, we get the output. So, firstly, the theory, we must to approve that resistor this is correct or not. We see that the output is must same with the voltage supply. Okay, we can see here that the output of resistor we get 10.606 voltage, and also same with the AC supply, voltage supply 10.607 VRMS. So it is correct, and also to prove that inductor and capacitor is correct or not, the same the output is must to the output of the inductor and capacitor must get same. So we can see here that we get 17,621 for capacitor and inductor 17.734. So it quite same, and so it's correct. And next we see at the current, we get 353.545 milliampere. So to see that we get the output is correct or not, we see at the our calculation. So we can see here that VRMS also we get 10.607. So the VRMS, so we voltage we get correct. Voltage inductor and capacitor also we get 70.65 quite similar, so it's also correct. And inductor we get 0.353 ampere. So we can see here we get 353.545 milliamperes. So also the output of current is correct. Okay, next, how to see that frequency is correct or not. The theory that we can see that frequency is correct or not, we must to click to AC sweep and run. So we can get a graph. We put the white background, and right. So here we click the cursor for this one, and cursor for the magnitude. Okay, how to get the frequency is correct or not, the theory of frequency is correct or not. We move this line at the 79.5, 79.5, And then at the face, we also move this line at the 79.5. So we can see here, okay. So we can see the line is same way, same line. So that prove that frequency is correct, theory of frequency. And next, to prove the impedance theory correct or not, we must to click here and click single frequency AC and run. Okay, so we get here the value of magnitude. We get 30, and also the resistor we get 30. Sorry. Okay, so that approve the theory of impedance also correct. So that's all from me. Thank you.